This is a joint work with Carsten Baum from Aarhus University, Bernard David from ITU in Copenhagen, Tora Friedrichsen from Alexandra Institute in Denmark, and Lorenzo Gentile, who's also here from ITU. A quick shout out to ResearchDAO, who made our travel to FC possible. Quick introductory slide on how MEV emerges. We have a simple blockchain interaction model shown here, where users submit their transactions to, let's say, a P2P network. The transactions are gossiped across the network publicly, and we can model this as a public transaction queue, which is visible to the adversary or visible to all agents in the system. Then we have a miner. The miner is extending the chain, as you know, and the miner will extend the sequence of transactions in a way that maximizes revenue, or maximizes profit. It has the power to sequence and also infer the transactions as they are publicly stored in the queue. So just to recap, we have the miner that has the power to infer user intentions from the pending transaction queue, but also obviously the public blockchain state. And it appends a transaction sequence to the blockchain constructed from the pending transaction queue and also its own injected transactions. So this essentially gives the miner, the adversary, the power to compute an optimal strategy and to execute it on-chain. And this is really the framework of our paper. We're interested in looking at methods which mitigate these two powers from the miner. So a very introductory slide to attacks, MEV attacks or front-running attacks. So here we have a interaction or two actions in sequence by user A against an AMM. And these two actions are identical. The parameters are chosen so that they're the same. And what I'd like to show here is simply that as they are executed in sequence, you'll see that the amount that the user receives for the same input amount, namely 15 units of tau 0, actually decreases with the second transaction. So this is, as you all know, is called slippage. This is something that we can use to perform front-running attacks, this phenomenon AMM. So let's just assume there's a third transaction that reverses the first two, namely the funds that are paid out in the third transaction are exactly the amount, the sum of the amounts that were paid in the first two, and vice versa for the other token. So the state of the AMM at the beginning, at the end of the sequence, is the same. So to illustrate what a sandwich attack is, let's just replace the user or the authorizer of the first transaction and the last transaction with M, the adversary. And we can easily see by summing up the exchanged amounts that, and here we're assuming that the price of the tokens is 1. They're both tau 0 and tau 1 have the same price. We can see that the adversary makes a profit of 5, which comes from the honest user that's sandwiched in the middle. So just a simple example of how a sandwich attack occurs with AMMs. Okay, I probably don't have to motivate why front running is a problem, but I'll do it anyways. So firstly, the honest users incur a financial loss. We just saw an example of a sandwich attack. Sometimes front running can also mean that there's some strategy that is stolen from an honest user that maybe was expensive to compute. Front running also generates, if you will, in quotes, unnecessary demand for block space, because the miner is injecting transactions into the transaction sequence or blockchain to extract front-running profit. And thirdly, we also argue there exist applications that simply cannot be realized without order fairness. One example we'll show are fairly scheduled orders in AMMs, and another one could be fairly issued NFT assets, which can be sniped by a front-running miner. Yeah, so the research question that we try to answer here is, can we obtain general transaction order fairness in public blockchains? Just a quick caveat, out of scope, the one thing that we don't cover are techniques which try to create unwinnable MEV games. So this is very informally of me, but what I mean by that is there exist ways or scenarios where the user can selectively choose its input such that the MEV is not positive. There's a paper here called Eliminating Sandwich Attacks with the Help of Game Theory that illustrates that quite nicely. So the profit gain from MEV does not exist, the cost of executing it. One could also design an AMM that takes that into consideration or into account. There's a paper by the group from Gervais, A2MM, which does exactly that. And so these types of techniques, here I'd really like to point out the paper here. There's a SoK called Preventing Transaction Reordering Manipulations in Decentralized Finance, which covers these kind of techniques, right? However, we still believe it's motivated to look at other mitigation techniques which remove the powers of the miner, namely transaction ordering and the inference of intent, because these techniques place a constraint on the application design and also a constraint on the user input space. Okay, so we've structured our presentation as follows. There are 3 types of mitigation groups that we're going to look at. We're going to start with fair ordering, which mitigates the power of the miner to sequence actions arbitrarily. So Klaus introduced this, but also Philip, I believe, before. There's a line of work that is looking at fair ordering consensus. And here I'm going to pick out one definition of order fairness from the line of Equidas, where we have called a gamma receipt order fairness. And so the idea here is that we have some group of nodes which are performing Byzantine agreement protocol, and they will order transactions based on the order they are received by these nodes. So we have users, A and M. They have transactions that they want to send or execute. These are sent via, let's say, authenticated channels to the nodes. And if a gamma fraction of nodes receives the honest user's transaction before that of the malicious user, then we have a guarantee that will be ordered before, modulo the dependency cycles which can't be resolved. But I feel this is a more easier definition to work with for this presentation. So if I can reach these nodes before my adversary, my transaction will be ordered first. But there are challenges here, namely first, these works tend to assume that the honest adversary has the ability to send the transaction via authenticated channel. And in public blockchains, generally we have a Gothic protocol. Transactions are gossiped across a P2P network. And there the network adversary can obviously rush the honest user, right? So this definition of receipt order fairness doesn't translate that well, I believe, to permissionless networks. So that remains an open challenge. Secondly, the honesty of the users running BA. So we have some honesty threshold that we assume here. But the transactions are public. So if the MEV bounty is public, assuming there can exist situations where honesty is actually irrational. So the incentive compatibility is also an issue in these kinds of works if the transactions are not blinded, right? So the next category we're going to look at are the batching of blinded inputs, as we saw before. If the transactions are public, then the bounty is out in the clear. So we want to blind the inputs, and then we want to batch the transactions such that the sequencing power of the miner is mitigated. So how would that look like? Very naively, we have some collection phase of blinded inputs, and then we have a subsequent phase where these inputs are executed. And just to quickly recap, why does this mitigate the powers of the miner? Well, the inference of user intent is taken away because the inputs are blinded, and the action sequencing power is mitigated because we might have some pseudo-random shuffling in the batch execution phase, or some input aggregation, which is specific to the application. Yeah, so we have in the collection phase a commit, a reveal. This reveal may or may not require some interaction by the user. We'll see a couple examples. And then the execution over public inputs. So here's I guess a motivating example with a naive example with hash commitments. So one could consider the users first committing a hash of their intended transaction. So we have the honest user here with the honest transaction. We have a malicious user with a front-run transaction, and a backrun transaction, which it hopes to be able to sandwich the honest user transaction. So these are committed to the blockchain. And then we have a reveal phase. And let's assume we have some pseudo-random sequence of these transactions, which is a function over these opened inputs. So in this case, the order of the sandwich is actually successful. And so all users, the honest user reveals the transaction, and so does the malicious miner. But the issue with like these hash commit and reveal schemes is, what if the miner sees, the miner always has the power to reveal last. And if the miner sees that the pseudo-random sequence is not in its favor, namely that the sandwich ordering does not succeed, then it can always abort. It cannot reveal. So we want to find a way to prevent these selective aborts. And one way to do that is potentially with threshold encryption. So this is a scheme that has been implemented by the Shutter network team. So we have, in the initial phase, a committee that runs a distributed key generation protocol and generates a key pair with a public key. Our agents now encrypt their transactions to that public key. So this is our blinded input. And in the subsequent phase, the private key is then opened, and the smart contract can then decrypt these transactions, or an agent decrypts these smart contracts, decrypt these transactions, and there is no way for the adversary to abort, right? The adversary has to accept whatever pseudo-random shuffling, whatever sequence that comes out of the pseudo-random shuffling, the adversary has to accept that. There's no way for the adversary to abort. We'd like to note that there are some challenges here in practice, some UX challenges. So let's assume a user B encrypts its transaction. So it's in the mempool, and it's waiting to be finalized. But it doesn't get finalized. It remains in the mempool beyond the end of the round. So this transaction here didn't make it into the blockchain, but because the opening of the private key already occurred here, the security scheme breaks for this user. It becomes public, right? So what does this user do? It may have to resubmit, but the intent of its transaction has been leaked. So that's potentially a UX challenge. Okay, but now we've introduced some committee, so there's some additional honesty threshold assumption. Can we get rid of that? And I think there is some hope, at least theoretically. So one can imagine having a delay encryption scheme. So here we encrypt to some fresh random string. That is, for example, this could be the hash of the previous block. So we're encrypting to an ID session. And any user that is willing to perform the extract step is able to produce the session key with which we can then decrypt these transactions. And so this does not require a specific honesty threshold. We can potentially incentivize some rational actor to perform this. And these time lock primitives are nice because they basically in theory they require that some agent performs D squarings or D random walks to which are not parallelizable. And so in the case of the delay encryption paper from DeFeo and Burgess, we have a really nice property. We can use a single session key. We only require the extraction of a single session key for all inputs. All inputs can encrypt to the same ID. We have a global reusable setup, and however, the implementation feasibility is still open question. Alternatively, we can use much simpler primitives. We can just use time lock puzzles where you have D squarings in an unknown group order, the RSW time lock puzzle. But that requires this agent here to perform as many extractions as we have inputs in a given round. We still have the same problem as before. If the encrypted transaction in the mempool doesn't actually make it into the blockchain, and the round expires, that transaction becomes public. So in our paper, we argue that batching is not enough. And the reason is the following. We have, let's assume the balances are public. So we have a standard public blockchain. The accounts are public. The balances of the users are known. And we have the users who are performing this encrypt-decrypt scheme. And let's assume these are swaps, like AMM swaps. It is possible for the adversary to pick the parameters of the swaps such that if the ordering outcome is not successful, that these actions are not enabled in the sequence and don't execute. So the only sequence that is valid is the one where the sandwich ordering actually succeeds. And this is possible because the adversary knows the swap direction of A. Let's say A only has one single token type, then it's obvious what swap direction is being performed. So if we need private balances, what can we do? So that brings us to the third category. We have private balances and also secret state. So the starting point here is the Hawk paper, Privacy Preserving Smart Contracts. What we have here is some underlying privacy preserving coin scheme. Coins here are generally modeled as commitments of some hidden value. And so we want the users to input or commit funds to this one-shot contract execution that involves some coin which commits some value. And we have some proof, validity proof that these coins are valid, right? That could be a range proof, that could be some set membership inclusion proof in zero knowledge. And furthermore, we have a contract manager which is off-chain, a trusted contract manager. The users perform a private input. They will input the parameters of the action that they want to execute, as well as the correct openings to the coin inputs, right? So we can ensure that these are consistent. The contract manager then obtains these private inputs and can then compute or output a new payout distribution across these three agents, including a validity proof pi A to pi C. So that's the starting point. Skip that real quick. And of course, if we don't want to rely on a trusted contract manager, we can replace that contract manager with an MPC committee. That's the basic idea. However, having to generate commitments or zero knowledge proofs inside the MPC is not practical. It's very expensive. But we know of a couple of teams that are working on this line of research where the commitment generation zero knowledge proofs can potentially be moved outside the MPC. So now we have a one-shot way of computing some function over private inputs and private funds. That brings us a little closer to what we want. And furthermore, we can have a secret state. So you imagine this MPC running multiple rounds. And in every round, we have the following. We have some private input from the user. We have some state, application state I. Some coins go in. And following the evaluation of that round, there's a possibility to output something private, to output coins, and also output something publicly. Now, this could be the price of the AMM or something like that. But importantly, the state carries over, the secret state carries over to the next round, okay? And we argue that this is quite nice, because consider an example where we have a user that would like to perform a very big swap. And maybe that swap incurs a slippage that is not acceptable. So the user decides to split that up to many smaller swaps, and the user would like to schedule these over some time frame. So for simplicity, we have just two swaps, one that should be performed in around R, and one that should be performed in around R plus 1. And so these are input to the MPC in round R. The first swap is performed in this round, and the second swap is performed in the round here. So the order schedule of the user remains secret throughout the execution, right? This could occur over n rounds. In contrast, if the public order schedule input by the user were public, then that can obviously be front run, because that can be seen. The adversary sees when a order is scheduled. So this is just to motivate the necessity for private state in DeFi. So that brings me to the end of our presentation. We talked about the miner powers and how how they can be mitigated, fair ordering, batching of blinded inputs to remove the powers of action sequencing and the inference of user intent. We argued that batching is not enough. We also need private balances, which we get from privacy-preserving smart contracts implemented with MPC. And we saw that with secret state, we can actually implement certain features which are not possible otherwise, such as scheduled orders or fair NFT launches, for example. Yep, thank you very much.